Project Euler problem number 3, we're looking for the largest prime factor of the 600 billion number. We know that every number is a product of primes, so for this, let's just call the first one P, and then the rest of them can just be called Q. We want P to be a divisor of n, which means that when we take n divided by P, there's no remainder. And so one way to find P is we can just start dividing a bunch of numbers and see when the remainder equals 0. So this technique here is called trial division, and the good news here is that it's going to work. We are going to find, in this case, the smallest prime factor first, but we can find all the prime factors like this. We just have to be really patient. As you can see, this is taking a long time just to find the first prime factor, and we're looking for the largest prime factor here. Now, there are some clever trial division techniques you can use. For example, if the number is not divisible by 2, you don't need to check 4, 6, 8, or other multiples, so we can get rid of those. The same logic applies to 3. Nothing was special about 2, so we can get rid of some other stuff. And there's some other trial division clever techniques out there, but we're going to do a different technique today. For now, let's just hold on to the 71 since we know it's a prime factor. Most importantly for us is this middle n is equivalent to 0 mod 71. That means when we divide by 71, we get remainders 0. We're going to use modular arithmetic into our next key concept, which is, what if I gave you this number d such that p divides d, but n does not divide d? That is going to result in the greatest common denominator of d and n being p. P divides n, because it's a prime factor. P divides d by our assumption. The GCD here should be p, or maybe some exponent p squared or something. But it will be something that divides n, which is not 1 or n, and that's what we want. And this is the key concept for the Pollard Rho algorithm, where rho is that Greek letter rho there with that shape. This algorithm relies on this infinite list of numbers. Here I'll do it mod 71, where each entry is the previous entry squared plus 1 divided by 71, take the remainder. And so there's only a finite amount of numbers. You can't have 72 show up, because if you divide by 71 and take the remainder, it's not going to be 72. That means we're going to get repeats. Here the first repeat is 58, and what's nice about these repeats is once something repeats, it's going to enter this deterministic cycle. And so here we draw this out in this way where we have this tail, and then 58 is the start of this cycle, which means once you hit the 58, you're on this circular path that you can't get off. Each number is the previous squared plus 1 divided by 71, take the remainder. And so this would just go on forever in a circle over and over and over again. Which is great. The only problem is we used 71 to build this, and all we really have, if I didn't tell you 71, was mod n, and n is huge, so our list actually looks like this. So what am I going to use this diagram in the middle for? Well, the 5th entry and the 16th entry are both 58 mod p, where p is 71. And so if I take the difference of them, then 58 minus 58 is 0 mod 71. So the difference of these two giant numbers up top is 0 mod 71. And when something's 0 mod 71, both its positive and negatives are, so we can just say that this 58,563,944,022 equals 0 mod 71. Pause the video here and figure out, why do we care about that number? That number is d. That p divides d, because it's 0 mod p, and n doesn't divide d, or at least we're hoping it doesn't. In this case, it doesn't. And so when I take the greatest common divisor, I get 71. To get the greatest common divisor, you would probably use the Euclidean algorithm, not part of this video, but we will need to calculate this iteratively, not just know that the answer is 71 here. What's great about what we just did is 58 wasn't special. I could have went next door to 28, update all of our calculations, and gotten a different d value. And the GCD of that d value and the 600 billion number, which is n, is also 71. And this will be true for every single entry around the cycle, which is important because this cycle was built, the shape of it, knowing 71 in advance. And we don't actually know 71 in advance. All we know when we start this problem is n, and our n is 600 billion. So what does that leave us with? it just leaves us with this ugly sequence along the right-hand side here. And sure, this thing's going to repeat, but more importantly, there are pairs of numbers in here that if we took the difference, we would get D. And while I don't exactly know what this shape in the middle looks like without you telling me the prime in advance, I know that shape exists. And so to find these pairs of numbers, we're just going to guess. And there's a clever way to guess so that we probably will succeed here, which is called the tortoise and hare method of detecting cycles, where the red box is going to increment by 2, and the blue box is going to increment by 1. And every time we guess, we're going to calculate the GCD and hope that it's a prime number that divides n. And we just keep going. To see here is the red is increasing by 2, the blue is increasing by 1. So once they enter this cycle, the red is eventually going to catch up to the blue, and here it catches up at the 11th entry, or in red's case, the 22nd entry. And so that is my D value, the 22nd minus the 11th entry, and sure enough, the GCD there is 71. And we can repeat this with that cofactor, that 8,400,000,000, etc. number of, I don't know what that shape looks like, but I know that red is eventually going to enter the cycle, blue will follow sometime thereafter, and then red will catch up to blue. And when that happens, we should get that the prime number falls out. Because I can't see that, we're actually calculating the GCD at every step, and that's what this table is showing. We're just guessing red go up by 2, blue go up by 1, until that number's not 1, and here it's 839. 839 is a prime divisor of this 600 million, but certainly not a number I want to find with trial division, right? And we can see the number of steps this is taking. In general, this algorithm takes smaller amount of steps for smaller primes. It normally finds the smallest primes first and then finds the bigger primes later, although it's not guaranteed to do that. And there's actually another value that could pop out of this, which is n itself. You can think about the conditions there. So sometimes this doesn't work, and you'd have to change your sequence of numbers here. But in this case, it did work, and we found our entire prime factorization in 71 steps, which is about how long it took us by trial division to find the first one. Coincidence here that 71 is on the screen twice. Two things to leave you with here is that 6,857 is a prime number. Question number 1 is, how do we know that? Okay, that's a non-trivial thing to figure out. And 2, what would happen if you did this Pollard Rho algorithm on the number 6,857? What would you expect to get? Thanks for stopping by. Thanks for listening. Go ahead, like and subscribe, and I'll see you next time.